Hello, math magicians. Today we're going to be looking at Bhaskara's second proof of the Pythagorean theorem. This is a pretty cool proof. I personally like it because we can do most of it with just a simple angle-angle congruence rule and constructing the diagram that we're about to show you with just a compass, a straight edge, and a pencil on a piece of paper. We first start by constructing a right triangle, and I will walk you through doing that. Each step we would do on our piece of paper. And if you consult your notes, you'll see more explicit instructions on how to do these different constructions. Now I'm going to remove this triangle and go through each step of the construction very quickly, just by revealing each point, as I've already constructed this in GeoGebra, but I urge you to construct it yourself on a piece of paper at home. So let's begin with a blank canvas. So first thing we will do is construct the right angle that we see in that right triangle. So let's first plot a point A, and we're going to draw a line F from that point. And then anywhere on that point, we're going to plot point B, the end of the line. Next, we'll plot a point C, anywhere above that line we want. And we'll draw a circle C with radius C to A. Next, we'll draw a line from E across C to the other edge of the circle as a diameter. And we'll plot another intersection, point G, which will then let us draw a line H from D to G, and it goes straight up. And we can see our right angle here. Now these two lines H and F we have will let us draw a triangle of any size we really want with a right angle down here at point D, or A. We label them both ways, just for convenience in GeoGebra. I'll overlay that original triangle here so we can see that it does line up with line H and line F. And I'll get a cleaned up version of this so we can begin our proof. So now we have our clean triangle here. We've labeled it with points A, B, and C in capitals and side A, B, and C in lowercase. We also see that this angle here is a 90-degree angle. Now next, we're going to construct an altitude. This might prove to be a little hard to do exactly with a compass, but you can do it given enough time and trying hard enough. So first, we're going to construct a line perpendicular to B and C. This would give us, of course, the fact that this is a right angle here. Next, we're going to mark the intersection point D, and then we're going to draw the segment H and remove the line just so we can have it clear. Now we see we have this one big triangle split into two smaller triangles. Let's examine this diagram real quick before we move on. We have this big triangle ABC made up of two smaller ones, ABD and ADC. You can see we have side C marked, which encompasses this whole side B to C. And then inside there's the smaller side S, just B to D, and R, D to C. And of course this is side A, this is side B, and the height is side H. Now we can look at either of the small triangles, GeoGebra allows us to turn them off, and see this is made up of side H and R. And if we turn T1 back on, we see this is B. And now for the other triangle, triangle 2, we see it's H and S, and then turning this back on, we have side A here. You may wish to pause the video while I show each of these smaller triangles and just copy down each part of it so you can have all three of your triangles separate from each other on your paper so you could see them all at the same time. Now we have to begin our statement reason proof to begin proving the Pythagorean theorem. So by construction, we know our angles, which I have labeled as Z, Y, and X on the left here, Y, X, Z. They are all 90 degrees, so let's just include that into our statement reason proof as a given. Given by construction. Next, well, let's examine our top triangle, triangle 2, and our bottom and our main triangle, triangle 1. So again, here's our top triangle. And we see that it does have in common with the big triangle, angle B. So it's safe to say that angle B is the same in both triangles, I believe. This is given by identity. Next, we can say that angle BDA of the small triangle, which we have labeled as angle Y, is congruent to angle BAC, which we have labeled as angle Z, of the large triangle because they are both 90 degrees. So let's write that in. Angle Z is congruent to angle Y. And that's because we know they are 90 degrees by construction. Similarly, of the other triangle, angle X would also be equivalent to angle Z for the same reason. So why don't we write that in as well? Both angles are right angles. Now we have shown that in the big triangle, T1, there are two angles similar to it in T2. That is the right angle and angle B, which they share. And the same goes for T3, the right angle and the angle C that they share. By the angle-angle theorem, we know that these triangles are similar. So let's write that into our proofs. Triangle ABC, our big triangle, is similar to triangle ABD, our top small triangle. And we also know triangle ABC is again similar to triangle ADC. These triangles are similar by the angle-angle theorem of triangles. Okay. Because these triangles are similar, it means that they are in ratio to each other. So if we were to take a ratio of the hypotenuse of the small triangle and one of its legs and compare it to the hypotenuse of a large triangle and one of its legs, we would find that they would be the same. So why don't we take a look at just the top triangle and we'll put it in ratio to the smaller triangle for now. So why don't we divide side S by side A. This is one of the legs and the hypotenuse opposite its 90-degree angles. Now let's take a look at this large triangle. Turn off T2. Well, the hypotenuse is C, and one of its legs would be A. We'll use A because it's the shared side. Makes things a little bit more convenient later. S divided by C. The sides are in ratio. Now if we do some math there, we can multiply the denominators of that fraction by A and C. This would wind up canceling out the denominator. So if we multiply S divided by A times AC, and we multiply A divided by C by AC, we then get SC equals A squared. This is just by algebra. Now let's do it for the other side. We're going to be picking the similar sides as last time. So looking at our smaller triangle, turning back this on, B seems to be the hypotenuse, and let's pick leg R. So now we'll have R over B, and we'll set it equal to the same thing on the bigger triangle. Let's turn that back on. Well, our hypotenuse is C, and we'll choose side B, the shared side. Again, the sides are in ratio. We're going to be doing the same algebra we did as last time to eliminate the denominators. So we have the denominators B and C, so we'll multiply both sides by BC. R over B times BC equals B over C times BC. And of course, when we solve that out, we'll get RC equals b squared by algebra. Now we should see something pretty familiar emerging if we have a squared and b squared. Let's start messing around with what we have down here. So this is what we have. SC equals a squared. We also have RC equals b squared. Why don't we add them up on both sides? So we get SC plus RC equals a squared plus b squared. Okay, let's factor this out. We can take out a c pretty easily, right? Do we see that on this side? So we get c times s plus r equals a squared plus b squared. Take a look at the drawing. This was side S in our triangle 2, and this is side R, and these two segments make up C. What do we get? Well, I think it's pretty clear that S and R add to C, so we get C times C equals a squared plus b squared. And what is C times C? C times C is, of course, C squared. So we have shown that C squared equals a squared plus b squared, thus proving the Pythagorean theorem. I'll scroll back up and make this proof bigger, just so you can take another look at it before we go. And don't forget to check your Google Classroom to make sure that you have all your homework completed for our next class. Thanks. Have a nice math day.